You are about to enter another dimension, a dimension not only of sight and sound, but of mind, a journey into a wondrous land of imagination. Next stop, the Twilight Zone. Fans of the 1960s television will recognize that as the lead-in to Rod Serling's Twilight Zone. Why did I use it? Well, it has to do with the fact that you're going to perform a laboratory experiment or an exercise, but you're not going to go in the lab to do it. You're going to have to use your imagination. And the purpose of this video is to give you the foundation and hopefully some of the tools that you'll need to complete this experiment and generate an acceptable formal lab report. So let's begin. Whenever you go into a lab, whether you're going to actually do the experiment yourself or have to work it the way we're going to do it today, because of the situation with the coronavirus, and everybody has to stay separate from one another, you need to keep your eye on the prize. And the prize in this case, is molecular weight, or another way of saying is molar mass. We're going to determine the molar mass of citric acid by using the method of titration. So you know what molar mass is. We need to work on titration and define it, and I've got a little video that'll show you the basics of titration. So what is molecular weight? Well, this is the prize. Molecular weight, or molar mass, is equal to the number, not mole, is equal to the mass of a compound, or an element for that matter, divided by the number of moles. So that becomes the mass, whatever that happens to be, grams per mole. Okay? So in order to get that information, you need to know what is the mass of your citric acid. And once you've determined the mass of your citric acid, then by our method of titration, you're going to determine the number of moles that that represents. So mass is the easy part. You just get that from a balance. But determining the moles is the hard part, or the unfamiliar part. And we're going to deal with that step by step. Okay, what is titration? Well, titration has many possible meanings. It depends on the unknown that you are attempting to identify. In our case, titration has to do with an acid-base reaction. And remember, an acid, our generic acid would be that, right, preceded by a hydrogen, at least one, some cases more than one, and then we're going to react that with a base that has a hydroxide on it, right? And it's going to produce a salt, right? So it's going to be like that, and water. So we're going to do this twice. In part one, we're going to standardize our base, and I'll talk about that a little bit more in a few minutes. And then we're going to take that standardized base and use it to determine the number of moles of citric acid. Okay, so there's the prize. The prize is molecular weight, or molar mass. And we need to know the mass and the moles. So if you keep your eyes focused on the number of moles, then the titration part will make more sense. Okay, so I'm going to share my screen and let you take a look at this video. It gives you the basics of titration, and then we'll try to make sense of it in terms of the experiment we're going to do today.
Professor of Chemistry at University. Today, we'll be discussing proper titration technique using the complete single burette assembly kit available from Carolina Biological Supply Company. This is the first in a two-part video series on titration. The purpose of the titration is to quantitatively determine the concentration of an unknown solution, commonly called the titran or analyte, by adding a volume of a chemical with a known concentration called the titrant. To mark the endpoint of a titration, an indicator is added to the analyte. Let's review some of the equipment that's needed for a titration. Carolina's complete burette assembly contains the basic equipment to get you started, including a burette, ring stand, and a burette clamp. A burette is a long, narrow, graduated tube used to add titrant. It has a stopcock to regulate the flow of liquid. Notice that the markings on the burette go from lowest at the top to highest at the bottom. The ring stand and burette clamp are used to mount and secure your burette. Other materials you will also need include a small funnel to help you fill the burette, a 125 milliliter Erlenmeyer flask, which works best for titration. The shape of the flask allows for more vigorous swirling than a beaker or other glassware and minimizes spill hazard. A volumetric pipette and pipette bulb to transfer a known volume of analyte to the flask. A wash bottle filled with deionized water, a beaker or flask of titrant and of analyte, indicator selected for your reaction, a reading card to help read the meniscus, and a sheet of white paper to help visualize the endpoint. To prepare your burette for the titration, it is good laboratory practice to rinse your burette thoroughly with deionized water, then with a small amount of titrant. After each rinse, open the stopcock to allow the liquid to drain out the bottom. If there is a lot of liquid clinging to the walls of the burette, then thoroughly clean your burette and repeat the rinse process. The accuracy of this technique is dependent on the titrant flowing into the flask and not sticking to the walls of the burette. Mount the burette in the clamp, making sure it is positioned vertically, and there is enough room to position your flask underneath the tip. Check to see that the stopcock is in the closed position. Insert the funnel into the top of the burette and fill with titrant almost to the top. Filling exactly to the zero mark is not necessary, but you do need sufficient titrant to complete the reaction. Check the column for air bubbles and gently tap to free them from the side walls. Remove the funnel. Place the Erlenmeyer flask under the tip and open the stopcock to allow a few milliliters of titrant to flow through, releasing any trapped air. Rinse the tip of the burette with water. Empty the liquid into a waste container and thoroughly rinse the flask. It is not necessary to dry the flask. Record your starting volume. It is important to accurately read the volume on the burette. First, note that the liquid forms a concave meniscus because the water pulls itself up the side walls of the glass. You should read the volume from the bottom of the meniscus at eye level. Secondly, it is important to read your volume to the correct number of significant figures. This burette indicates volume to the nearest 0.1 milliliters. With any graduated glassware, record the volume to one additional decimal place beyond the smallest graduation. In this case, record the volume to the nearest hundredth of a milliliter, estimating the final place. Use the volumetric pipette to transfer the analyte to the flask. Add a few drops of indicator to the flask and swirl. Place the flask under the tip of the burette. Record this volume. Placing a piece of white paper under the Erlenmeyer flask may make it easier to detect the color change. Operating the burette requires two hands. One hand turns the stopcock, while the other hand swirls the flask. Practice turning the stopcock a few times to familiarize yourself with how quickly the flow starts and stops. It is common laboratory practice that the first titration is an estimate. Open up the stopcock and allow the titrant to enter the flask quickly. Continuously swirl the flask. As the volume of titrant in the flask increases, the color of the indicator appears, then disappears as you swirl. When the analyte becomes a colored solution, close the stopcock. Record the final volume of the burette. Subtract the initial volume from this final volume to get the estimated volume of titrant needed for this titration. Knowing the volume that is a little past the endpoint, subtract 5 milliliters from that number to get the amount of titrant that can be safely added before a slower addition is required. As the estimate titration shows, a dark-colored solution indicates an excess of titrant has been added. The desired endpoint is a pale, faintly colored analyte. To reduce the risk of passing the endpoint, slow down the addition of titrant when flashes of color begin to appear in the analyte. Adjust the stopcock to slow the flow of titrant to a drop-wise rate. Continue to swirl the flask with one hand and keep the other hand ready to close the stopcock. When you notice the indicator taking longer to fade, close the stopcock. Rinse the tip of the burette with deionized water and swirl the flask. Record the final volume on the burette. If the analyte remains faintly colored, then you have reached the endpoint. If the analyte is still colorless, then repeat these steps. Add a drop, rinse, swirl, and record until a faint color persists. Typically, titrations are performed in triplicate. Use the average volume of the titrant required to reach the endpoint for any calculation. You now know how to properly perform a titration. Be sure to check out the second video in this series. In that video, we will go over the proper procedure for determining the concentration of an unknown acid solution using a base of known concentration. Carolina has everything you need for your chemistry lab. Visit us at carolinachemistry.com to see our complete line of products and kits for chemistry.
Okay. So there was a little propaganda in there from Carolina Biological Supply, but it's basically a pretty good demonstration of what a titration is for the base, which is the titrant in your burette, being titrated against an acid, which is in the Erlenmeyer flask. The indicator that was used and was not named was probably phenolphthalein. It's commonly used for acid-base titrations. It's not the only one, of course, but it's the one that we will use in this exercise. Okay. So, the titration technique is a critical skill, and I'm really sorry that we're not able to do it in the lab, because it's something that is best acquired hands-on. But that being said, we'll try to deal with it theoretically and dip our toes in the twilight zone from time to time and get enough information so that we can continue with part 2. Part 1, we will titrate. So for part 1, we're going to titrate our base, sodium hydroxide solution, plus an acid, which will be, and I'm running out of board space here, our acid, which is that one. And hopefully you'll recognize that as acetic acid. Okay. The solution of sodium hydroxide is the one that we're going to use to titrate against the citric acid later. But sodium hydroxide in storage is not very stable. Sodium hydroxide itself will absorb water from the atmosphere. So, and no container is completely, no plastic container anyway, is completely sealed. So it may absorb some water over time and dilute the solution. So we don't know exactly what the concentration of this sodium hydroxide is, even though it may state a concentration on the bottle. Another reaction that occurs is sodium hydroxide will react with carbon dioxide in the atmosphere and produce sodium carbonate. Which is a solid, and it will precipitate in your solution. It will take the sodium out of solution, it will neutralize the hydroxyls, and the concentration by this mechanism will also decrease over time. So we need to know exactly what the concentration of sodium hydroxide is at this moment when we use it. And that's why the first titration, part 1, is going to be with sodium hydroxide against acetic acid. And the acetic acid in the method is a fixed concentration of 0.873 molar. Acetic acid over time is very stable in solution. So once this has been determined, it stays that way for years on end. So we will use a standard solution here to determine the concentration of our sodium hydroxide. Now, how do we do that? Well, we could use stoichiometry, right? This base reacts with that acid and produces this salt plus water, right? Hydroxyl plus a hydrogen makes water. And we could use the stoichiometry to determine our unknown. But there's an easier way. Since there's only one hydroxyl and one hydrogen involved in this reaction, we can use this formula. The molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. And we can do that because there's a one-to-one relationship, 1-to-1. When we get to the citric acid, we have to adjust our thinking some. But for now, this works fine. And remember that if molarity equals the number of moles in a unit volume, then rearranging our equation where molarity times volume is equal to the moles, and the moles of the acid equals the moles of the base. Okay? And that's what we're doing in a titration. When we reach the end point, that is when the color changes from clear, the acidic form, to faint pink, slightly basic, we have reached the point in which we've neutralized this one is equal to that one, this one is equal to that one. And once we know how many moles of base are in the Erlenmeyer flask, all we have to do is divide that by the volume. And the volume in this case, in this experiment, is going to be 25 milliliters, right? So the volume of the acid is 25 milliliters, but you'll recall that you can't divide milliliters into moles and get molarity. The definition says moles per liter. So you have to change this to liters, which is 0.025 liters. once you've determined the moles from our titration, because this is fixed, this is determined by the titration. You'll read it off the burette. This is unknown, and this is fixed, 25 mils. So all we have to do is solve our equation for this one unknown, and now we will have, excuse me, I got that backwards. Acid is known, base is not known. Then we know we can solve for the unknown molarity of the base. That's part one. Okay. Now recall from the video, it may have not been obvious. How do you determine the amount of titrant delivered during the reaction? Well, the burettes are calibrated not from bottom to top, or from top to bottom. So 0 is up here. And for our burette, 50 milliliters is down there. Right? So you have to read it from top to bottom. And if you go past a value, say if you're down here around 10, but your meniscus is here, it's not 9, but it's greater than 10. So it's 10 point something. That's the first trick in reading a burette. The second is you have to understand that the volume that you deliver, or the change in volume, is equal to the final volume minus the initial volume, right? So the initial volume, if you set it up this way, your initial volume could be 0, in which case that's 0, and whatever you read off of here is actually the change in volume. That's the value you want for your volume. Now, if you do a triplicate titration, the final volume for the first titration becomes the initial volume for the second titration. Okay, so you fill that in your table as final, initial, right? So each of your titrations, say you start off with 0 here and you end up with 10.0 there. Well, 10.0 here is for the next one. And then you end up with maybe 20 for that one. And 20 becomes this one. And then you have some value there. Right? That's how you efficiently use a burette. Okay. So now that we've determined the molarity of our sodium hydroxide, we can move to part 2. And we're gonna work through some discussion questions in the hard copy method to reinforce these ideas. So don't panic. And this is being recorded, obviously. Why would I waste my time without recording it? So part 2 of this exercise, we're going to use our standardized base, which in part 1 was in the burette, and in part 2 it's still in the burette, but now instead of the unknown concentration being in the burette, the unknown is in the flask. We know the concentration of our sodium hydroxide in the burette, and we're going to deliver a certain volume of that to neutralize the citric acid in our flask. And then we can tell by this relationship how many moles of base were delivered to neutralize the acid. Then we need to know the relationship between the number of moles of base and the number of moles of acid. And I'll talk about that in just a second. But in part 2, the flask is going to contain our citric acid. And it will be a known mass, equals so many grams, an exact amount. On our balance in the laboratory, you can measure this out to 4 decimal places. And the more decimal places, the better. But we can't titrate a solid with a liquid. We have to titrate liquid and liquid. So all you have to do is follow the method and add some water to the flask and dissolve the citric acid. The method gives you those details. I won't bore you with those details right now. Once the citric acid has been dissolved in the water and you add some more indicator, your phenolphthalein, then you're ready to titrate. And the procedure is exactly the same as before. You titrate until you get the faint pink color, right? Because phenolphthalein in this solution is going to be clear, right? The phenolphthalein is going to be clear in acidic solutions, and it'll be pink in basic solutions. Right, so the faintest pink is the best because that gets you closest to the actual equivalence point for acid neutralized by base. That's a distinction that we've made in the lecture. The equivalence point is the actual point where acid equals base, exactly, to as accurate a measurement as you can make. Whereas the end point is that point at which the color changes. You try to get these two as close to one another as possible. They won't be exact. But for phenolphthalein, the color change starts at about 8.3 and persists until about 9 or 10 in that range. So the difference in volume that's incurred by using this indicator versus another one is so small that it's a reasonably good indicator for any acid-base reaction that we're going to investigate. All right. So you add volume of base until citric acid is neutralized. All right. So now we know how much base was added. We know the moles of base that were added based upon this reaction. Here's the citric acid. I believe that's right. This is citric acid, and I'm not going to write aqueous up there because I don't have enough board space. So everything's in solution. Then we're going to add sodium hydroxide in solution. This is our standard. And the reaction then is going to produce like any acid-base reaction, acid plus base makes salt plus water. But this is not balanced. Notice we have 3 hydrogens on every molecule of citric acid. There's the fly in the ointment. In order to balance this, we need 3 positives here to replace those 3 positives, which means you need 3 here, which produces 3 hydroxyls, 3 hydrogens, 3 waters. Okay, so now the stoichiometry is a bit different for this reaction. In other words, for every mole of citric acid, it takes 3 moles of sodium hydroxide. So when you determine the number of moles of sodium hydroxide by your titration, you've actually only neutralized 1/3 of that many moles of citric acid. Right? It takes 3 times as many moles to neutralize a mole of citric acid. So our relationship then becomes molarity of our sodium hydroxide times its volume gives you the number of moles of base. But the relationship then, I think there's a better way to do this. Let's do it stoichiometrically, right? So we know the number of moles of base. What we don't know is the number of moles of acid, right? So if we know the number of moles of base, then we need a conversion factor that cancels the moles of base and leaves us with citric acid. I abbreviate Ca for citric acid. All right, so what's the relationship? Remember, 3 here, 1 here, right? So if we know the number of moles of base, we actually only have 1/3 the number of moles of our citric acid, right? There's our conversion factor. For 1 citric acid, you have 3 sodium hydroxide. And the conversion then gives us 1/3. Actually, this one divided by 3 equals the moles of citric acid. So when you determine the number of moles of base by molarity times volume, then you divide it by 3 and you get the number of moles of citric acid. Okay, remember the prize? Keep your eye on that prize. The molecular weight is equal to mass divided by moles of citric acid. Now we have the moles of citric acid. Okay, that's the theory. Now what you need is the data, the numbers, to do these calculations. So that's where I come in. And those numbers are provided for you in Blackboard in the same folder where you will find the hard copy for this method. And let me see, I can share that screen, I believe. Here we go. So let me share this screen and I'll show you where that information is located. Okay, here we are. Well, this is the instructor's view, and I need to do that because I haven't made the data available yet, but I will show you where it is. Okay, this is your starting point. You recognize this as Start Here in Chem 103 Blackboard. Scrolling down to lab exercises. And then our exercise is this one. And there's your hard copy for the method. It's best to open this up like that. And then to access this hard copy, right-click it and save link as and put it anywhere on your computer. Then you go access it with your Adobe Reader and print it. Okay, so let's go back. Here's the data, right? I haven't shared it yet because I need to play with it a little bit, so I don't give you all the answers. But it's actually a photograph of a whiteboard in the lab for a previous semester, where we actually collected the data, and it looks something like this. Let's see. Right. You're not going to be able to see this until I stop the share. So let's stop the share. Here we go. So this is what it will look like. See, there's a whiteboard, and you can see all the paraphernalia down here. This is part one, right? And notice there are two groups. There were two groups in this lab. So you can use either one you want, and I'll probably leave this information down here. This shows the calculation of molarity for the base, right? We have to standardize the base. That's what it's called. We standardize the base against a known acid, which was acetic acid, and its concentration. And it uses the same formula that I gave you just a few minutes ago. What you'll also notice is that with that formula, just a generic this side is equal to that side, and if the volumes are in milliliters on one side, they have to be in milliliters on the other side. So when you use this equation, you don't have to change the volume to liters, because milliliters will cancel. It's a ratio, right? So you can save yourself a step, trouble. If you want to convert it to liters, that's fine. It'll work either way. But if you have so many milliliters of this one and so many milliliters of that one, then when you solve for the unknown, right, the milliliters are going to cancel. That's why when you finally get a look at this data and those calculations at the bottom of the whiteboard, you're going to see that milliliters were not changed in this process. And that's because they will cancel. It's no problem. You're still going to get molarity. Now, when you actually do the calculation for molar mass, you do have to be sure that you use liters in your molarity in order to get the proper number of moles. Otherwise, you'll be off by a factor of 1,000. Okay. So notice on this whiteboard, part 2 is not filled in yet. This was only part 1 that was accomplished. So in part 2, this part is still up on the board right here with group 1 and group 2. Pick a group, right? It doesn't matter which one. And then these are the calculations using that stoichiometry for the base and citric acid. And I go through some calculations here. Here's the accepted value that you're going to compare right there, the accepted value for the molar mass of citric acid, and you will compare yours against this value. Now these calculations, I'm not sure, I may get rid of those because that gives you everything and doesn't require any firing brain cells on your behalf to get the work done. So those will probably disappear in the final version. But we're going to go through some discussion problems now that are in your hard copy document. And this is on, it may not be in your copy. Let's see. No, you only have laboratory questions in your document right there. These are discussion questions to help you deal with the calculations. So we have 2 sets. One is a pre-lab set and a discussion questions. Let's do the pre-lab first. Okay. Now I'll have to give you the questions as we go along. I'll tell you what, I'm going to erase all of this because we need the space. All right, for our first pre-lab question. It says, calculate the molarity of sodium hydroxide solution if 24.3 milliliters were required to titrate 25 milliliters of a 0.873 molar acetic acid solution. So this is actually what you're going to be doing in part 1. This is an example. All right? So what do we do with a word problem? First thing you do is extract the information and put it on the board in a form that looks more like a formula. Right? Get the information out of the problem so anything in here that you don't need is left behind. All right, so what do we know? Well, we know that the volume of, we don't know the molarity of the base, right? That's unknown. That's what we're looking for. But the volume of the base that was delivered to neutralize the acetic acid is given. So the volume of the sodium hydroxide is 24.3 milliliters. Now, in the Erlenmeyer flask, we had delivered exactly with a volumetric pipette acetic acid. We had delivered exactly 25.0 milliliters. And we were given the molarity of the acetic acid as 0.873 molar. Okay? Now, notice M1V1 equals M2V2. This one times that one should equal this one times that one. Right? So if we solve for the unknown, then we're going to have right? This used to be over here times that. So now we can fill in the numbers here. I might have to write small. I hope, yeah, I think it'll pick it up okay. So the molarity of the acid is 0.873. The volume is 25, and the volume of the base is 24.3. Remember, these are both milliliters, so they cancel, right? No problem. You still get molarity. So if we do the calculation, what we will determine is that the molarity of the base is 0.897 molar. Okay. All right, that's pre-lab question 1. Pre-lab question 2 takes an example of a titration with citric acid, right? So we're going to work out in pre-lab question 2 the steps that you would use once you get your data, or actually the data that I delivered for you to use in part 2. All right. So here's pre-lab question 2. And what information are we giving? We're asked to calculate the molecular weight of citric acid. Right? We don't know what it is yet. we are given the volume and the molarity of the base. Right? So the volume of the base, which is sodium hydroxide, is 25 mils. And the molarity of the base is 0.750 molar. Okay, those are given. We're also given the mass of the citric acid, right? 1.20 grams. That's everything that's given. And we're asked to calculate the molecular weight, right? So remember the prize. The molecular weight is equal to mass divided by moles. Right? So we have the mass right here. We need to calculate the moles based on this information. All right. So how many moles of base were used in this experiment? Well, the moles are going to be the molarity times the volume. So the moles of base equal the molarity times the volume. But the volume has to be in liters this time because we don't have a ratio. We just have this single calculation. So how many liters of base were used? 0.025 liters. Now that calculation will give you moles of base, which happens to be 0.0188 moles of sodium hydroxide. Okay? Now remember what we said. It takes 3 times as much sodium hydroxide to neutralize citric acid. So we actually only have how many moles of citric acid? Well, our conversion factor, right? For every 3 moles of sodium hydroxide, you have 1 mole of citric acid. So we have to divide this number by 3, right? 3 into that number then equals the moles of citric acid, which will be 0.00627 moles of citric acid. Now we have mass, moles, mass, moles. We can calculate the molecular weight, molar mass of citric acid. The number of grams is 1.2, and the number of moles is 0.00627. And we get 191 grams per mole, That's our determined, that's the experimental value for our citric acid. We would compare that to the actual value, or the accepted value for citric acid. Is 192.13 grams per mole. Accepted. Okay? So you remember how to do percent error, right? It's this one minus that one divided by that one times 100. This one looks pretty close. If you get anything less than 5%, then I'll be very happy. Okay. So those were the pre-lab questions. Number 1 gave us calculations for part 1. Number 2 gave us calculations for part 2. Now, let me take a look at the discussion questions and see if they're actually something that will be worth considering. Actually, discussion questions 1 and 2, they just turn the calculations around. And I think we'll skip those. You don't need to deal, we're not going to deal with the discussion questions. These pre-lab questions give you all the tools you need to do the calculations with the data that I give you, and then generate an acceptable formal report. Okay, remember, you only have to choose one of those groups. You don't have to choose both of them. Just one group, whichever one you want. And it doesn't have to be the same one that other members of your group pick, unless you want to. Since you're not actually doing the experiment together as a group, then there's no sense in holding you to that for this purpose. But when you generate your report, here's the twilight zone. Imagine yourself as being there, doing the experiment, gathering the data, and then generating the report. So that means you put all this stuff in your lab notebook as if you actually did it. And then when you generate your report, remember, one of the things that one of my pet peeves is when you write the procedure, you write it in third person, passive, past tense. That is, when the method says do this, then when you write your report, you say this was done. All right? And that should give you a fairly decent report, even though you actually didn't do the experiment. But those are the costs of dealing with quarantine. Okay, since you're not actually here, you can't ask me any questions, but if you have questions, you can either text me, call me. You can call my office phone and leave a message. Those messages are still converted and sent to my email address, which I will get on my cell phone. Or there are office hours that I'm keeping now on Zoom, and I sent everybody an email. So you probably want to look at your emails occasionally. I know it's hard for some students to do. Get away from your personal emails, get back to New River email, look at them at least once a day. And for those, my other students, my Southern students, go to your Southern address and look at your emails at least once a day. Twice a day is better, so that you can catch any updates that I might deliver. I might deliver some in the morning and some in the evening. And if you wait till the next morning, you won't get those. And that just puts you 12 hours behind. Okay, so I sent you an email and it had changes in my office hours. If you look at my schedule, right, remember this thing right here? Look at my schedule for the office hours. Those office hours are good except for the changes that I made. And I sent you those in an email. So if you need to connect with me by Zoom, then I gave you the particulars. I gave you the web address to go to your browser, use that web address and the ID that accompanies it. The first time you use it, you may have to install the client, but after that, it should connect fairly easily. And then you can interact with me through video and audio. All right. So that's all I have on this. This was molecular weight of citric acid by titration. And the method is in Blackboard. I showed you where that was. And very shortly, I will make corrections to the data and then post the data also. So you'll have that and the data, and you should be able to generate, do the calculations, generate your report. So that's all I have to say about that. And there we are, leaving the twilight zone.